Can't hear you because of microphone yours.
Good morning.
Good morning.
Good morning.
And happy Easter.
Good morning.
Morning.
Dear colleagues, today we are going to record our traditionally provided webinars where we would we would like to present some results obtained under the project which is funded under Horizon program fellowship, Horizon 2020, and
I'm sorry.
Yeah.
Recording. Sorry.
Yeah, recording started already. And first of all, I would like to present our partner from Hungary. This is Associate Professor of Department of Process Engineering and Head of Chemical Engineering Program at the University of Pannonia, Faculty of Engineering, Attila Egedy. Thank you very much to be present today, to join us. Want to be in contact more often, more times than we are, but because of. Don't focus on the situation in the world, but because of. Some of us are currently in Kharkiv. Maybe happens some situation with some alarm. It may influence on our recording process, but keep calm. Let's continue. And beside of all our group who currently work in the project, also we invited our colleague from the University Kharkiv Urban University, named after Beketov, Associate Professor Yevgen Tsegelnyk. Hello, Yevgen. Show us your face, please. Hello. And today we want to present two works which was obtained under the project. Or should I name each of us? Me as a principal investor, Olga Shipul, and my colleagues Vitaly Mintyuk, Vadim Garin, Oleg Trifonov, and Denis Tkachenko. Thank you, my dears. Thank you that we are together always. And our works, first we will start with smoothing of a liquid surface by surface tangent forces. Will be presented by Denis Tkachenko. You are welcome.
Yes, thank you.
Share your screen, please.
Yeah, I need a few minutes, few seconds. Can you see my screen, desktop?
Yeah.
Yes.
Yeah, okay. So let's start. Hello, my name is Denis Tkachenko, and I will present our study titled Axisymmetric Problem of Smoothing the Surface of a Viscous Liquid by Surface Tension Forces. In high-precision industries, surface defects on thermoplastic parts, common after processes like injection molding and additive manufacturing, can significantly impair performance. Traditional finishing methods often fall short, especially for complex geometries. The impulse thermal energy method, or ITM, offers a promising solution by using controlled heating to melt the surface layer, allowing surface tension to smooth out irregularities. However, a lack of predictive analytical models limits its industrial use. This work addresses the challenge by proposing a model to estimate leveling time for axisymmetric surface defects, helping improve process control and efficiency. This study builds upon Orchard's classical solution by extending it to the axisymmetric case, relevant for post-processing thermoplastic parts using the impulse thermal energy method. In this context, surface leveling occurs during a brief but intense thermal pulse, which melts the surface layer of the material. The resulting flow is driven by surface tension, allowing the irregularities to smooth out. The primary objective is to determine the characteristic time required for a protrusion or defect to level out. This time is crucial for calculating the optimal thermal energy input. Too little results in incomplete smoothing, while too much risk damaging the part. A simple analytical model offers a clear advantage here, as it allows the leveling time to be expressed explicitly, supporting efficient and controlled ITM process. Unlike Orchard's original planar formulation with periodic waveforms, the current work addresses an axisymmetric geometry more representative of real-world part features. At this small physical scale, on the order of 1 millimeter, gravitational and inertial forces are negligible. Surface tension dominates, and the fluids is treated as Newtonian and purely viscous. The mathematical model is based on the Navier-Stokes and continuity equations in polar coordinates adapted for an axisymmetric configuration. Given the small scale and low velocities involved, we neglect gravity and inertial effects, focusing solely on viscous and surface tension forces. Boundary conditions include no slip at the bottom surface and stress balance at the free surface, where surface tension is described using the Laplace equation. Due to axisymmetry, the surface curvature is determined by two principal radii derived from the free surface tension, surface function. Symmetry conditions are also imposed at the radial boundary. Together, this forms a complete model for surface leveling driven by surface tension in a viscous liquid. To solve the problem, we apply separation of variables in the axisymmetric domain. Use of Bessel functions as the basis. The velocity and pressure fields are expanded into a series that automatically satisfies the boundary condition at the symmetry axis. Substituting these expressions into the governing equations reduces the system to ordinary differential equation in the vertical direction. These are then integrated, yielding closed form solutions that depend on the small set of integration constants. The constants are determined by applying boundary conditions, including the stress balance at the free surface, where surface tension acts as the driving force for leveling. The shape of the surface is expanded into a Bessel-based Fourier series, and under the small gradient assumptions, the curvature simplifies accordingly. This process leads to an explicit differential equation for the amplitude of a surface irregularity. Its solution, shown in the final formula, demonstrates exponential decay of the amplitude over time. The decay rate depends on material properties, geometric parameters, and the function phi of theta, which captures the effect of layer thickness relative to the feature size. Compared to the planar case described by Orchard, the axisymmetric formulation shows a faster smoothing rate due to the added circumferential curvature, which increases surface tension driving pressure. To validate the analytical model, we compare it against numerical results obtained using the incompressible smoothed particle Galerkin method implemented in LS-DYNA. This is a meshless Lagrangian-based approach tailored for simulating viscous fluid with free surface, surface tension, and surface structure, fluid structure interaction. In our simulations, 1/4 of the domain is modeled with radial size 5 millimeters, and Newtonian liquid with properties similar to cooking oil is used. To eliminate inertial effects entirely, the fluid density is set to a negligible value of 1 kilogram per cubic meter. Free slip is imposed along the vertical boundary with a 90-degree contact angle, and a no slip condition is applied at the bottom. Simulations were performed across a range of average layer thickness at initial amplitudes, enabling a comprehensive comparison with the analytical predictions. A qualitative comparison of the analytical and numerical solutions is shown using the velocity and pressure distributions at the initial moment for a representative case. Both approaches capture the same overall flow pattern, radial velocity peaks near the center and close to the surface, while vertical velocities are concentrated at the center and edge of the free surface. Pressure profiles show similar distributions with minimal decay into depth. Amplitude evaluation over time was also compared to assess the analytical model's accuracy. The focus was on the simplification introduced at the upper boundary, applying boundary condition at z equal 0 and rather than z equal free surface coordinate, using simplified stress components and neglecting curvature denominator. These are absent in the numerical model, which solves the full system. Next. For quantitative comparison, the curves were linearized using the least square method. The results confirm that the assumptions of a smooth free surface holds for a wide range of cases. For moderate and thick films, the analytical solution is reliable up to a relative initial amplitude of 40%, with errors below 10%. However, for thin films, significant disparities appear, with the numerical model predicting a faster smoothing rate unrelated to the free surface smoothness. In the heat treatment of plastic surfaces, the temperature distribution follows a heat flow equation, and in the molten surface layer, it's approximately linear. If fluidity is assumed to be proportional to temperature, viscosity varies from a finite value on the surface to infinity at the solid phase. In this case, the governing differential equations are modified to account for the variable viscosity. The solution involves functions with modified Bessel function, which describe radial and vertical velocities as well as pressure distribution. The time-dependent amplitude is determined similar to the constant viscosity case, but with a modified function that accounts for variable viscosity. This results in slower smoothing rates due to the high average viscosity. The difference between the variable and constant viscosity functions is shown, demonstrating the reduced smoothing rate with variable viscosity. The same solution applies to periodic inequalities with adjusted parameters for the specific geometry. To conclude, we have extended Orchard's formula to address axisymmetric problems, allowing us to develop an analytical solution that aligns well with numerical results for moderate and thick layers, where the thickness exceeds 20% of the radius. This solution remains accurate for initial surface amplitudes up to 40% of the radius. We also derived an analytical approach for variable viscosity across the liquid layer, which applies to both periodic and axisymmetric problems. This provides us with a straightforward method to calculate the time required for surface smoothing. The primary goal of our work is to determine the surface smoothing time, which is defined as the time needed to reduce the surface roundness by a factor. Using the derived formula, we can calculate this time considering factors like dynamic viscosity, surface tension, and the surface shape. For surfaces that deviate from standard Bessel or cosine shapes, we can approximate the smoothing time by using the first term in the Fourier series expansion of the surface shape. Thank you for your attention. I look forward to any questions and or further discussion on this topic.
Thank you, Denise. Thank you for your presentation. Can't see any hands up for asking questions, as minimum up to now,
Maybe in private speaking conversation.
or after the second hour presentation. Maybe they would be a joint question, or how should we implement this result accurately to the topic of our project, or like that. Thank you one time more, and let's continue. Our second presentation would be presented by Oleg Trifonov. The title will be pronounced by him. Do not repeat it several times. You are welcome, Oleg.
I will share my screen. Do you see it?
Yeah.
Okay, dear colleagues, let me introduce results of our research within the Horizon project. The topic of our investigation is CFD simulation of plastic parts melting during the thermoenergic processing, taking into account temperature-dependent plastic properties. We already did some tries to simulate melting process within the thermal processing of plastics, and we used such a parts which you see on the screen. And specific features of these parts exist of some small parts like bars on the top face and on the edges. This samples needs to investigate the influence of size, part size, and some small object size on the melting process. And it is important at plastic treatment, because of at plastic parts productions a lot of such parts, such bars can be formed during the processing. But previously, during our previous simulations, we used some assumptions. And first assumption is general constant properties. So the properties of plastic, and we have used polycaprolactone PCl plastic. So properties were constant. So all of them don't depend on temperature. Another assumption was constant temperature conditions inside the chamber. So we assume that initial we have temperature which corresponds to the combustion products after the combustion, but the distribution inside was uniform, and we don't take into account flows, velocities inside the chamber after combustion. And very briefly, results show us that liquid formation, liquid means we can observe melting of the parts exactly on the small elements and on the edges. But to improve the CFD model, which was developed for this simulation, we decide to apply more advanced conditions. First of all, for some initial temperature conditions and initial flow conditions, and next we try to apply temperature variable properties for our plastic material. For the first conditions, if you talk about the temperature inside, we apply exact temperature and flow field after the combustion. That distribution was obtained exactly after the simulation of combustion inside the chamber. Combustion model was verified, and we assure that temperature distribution inside the chamber is correct. Some validation results we can see on the screen, and this experimental investigation was carried out with support of our partners from Warsaw University of Technology. Our colleagues provide us experimental equipment and help us to carry out that experiments, and that results was very useful for development of correct simulation model. So as a result, we obtain initial temperature distribution, and initially we use temperature exactly after complete combustion. So the moment where when all fuel mixture was combusted. And now we see that temperature distribution is really ununiform, and moreover we have flow a lot of fluctuations and turbulences inside the chamber after the combustion. And this flow field, of course, will influence on the heat fluxes inside the part, and is a very important development of simulation model. Another very important stage was determination of temperature-dependent properties of the plastic. Temperature-dependent properties also were obtained with support of our partners from Warsaw University of Technology, by our colleagues from Faculty of Power and Aeronautical Engineering, Institute of Heat Engineering in Poland. Our colleagues helps us to find heat capacity, thermal conductivity, properties, independence of the temperature, and these properties are very critical for correct simulation of melting process at thermal processing. And if we look on this screen, we can see the melting process, simulation of melting process, but to define the influence of temperature-dependent properties, we have simulated two cases. First case is application of the real distribution of temperature and flow field inside the chamber, but constant properties of the plastic. And the second, more complex, it is real temperature and velocity distribution and temperature-dependent properties. So on this screen we can see the result for case with constant properties, and we see that very fast boundary layer of the part will heat and melts. After about 0.1 second of holding time, almost all surface is almost melted. If we compare with the results at unmovable temperature conditions and uniform, we see that after 2 seconds we have melted only bars and edges. It means that flow field near the surface, near the body, is very important, and increased velocity, of course, increase in velocity also causes increasing of heat fluxes. That's why we can see that after 0.1 second we almost melt surface, almost all surfaces on our parts. But after applying temperature dependent properties, we see a bit different picture, and we have found that process of melting is not so fast, and within the same time we can see that melting take place only on the bars and small elements of the parts. One more again. It means that temperature-dependent properties sufficiently influence of the simulation result, and we observe approximately the same picture at experimental investigations, which will be presented on our further articles and publications. And for some comparison, we can see that influence of temperature-dependent properties is very important. For constant properties, during the same time, we have almost all melted surfaces. For case with temperature-dependent properties, we melt only the small features of the part, like bars on the top surfaces and on the edges. The same if you look on the depth of the melted layer, we see that for constant properties it's much bigger. So, if you talk about the conclusions and further investigations, we still understand that the simulation of plastic melting process is very complex and resource-intensive task. Application of temperature-dependent properties increase simulation time about maybe 10 times, because it requires less time step for a simulation. Of course, temperature-dependent properties are very important, because that properties allows us to represent real melting process. But for development of completely correct model, we need improve it, and it is our further tasks. And some of them is, first of all, investigate the effect of holding time more detailed. It needs carried out some additional experiments, and for this we need more exact control the holding time. Another very important is process of product release, combustion product release, because at release combustion products, velocity inside the chamber increase. It is also may increase the heat fluxes, and this process can affect on the melting process exactly during the product release, and it is important to allocate our parts far from that fast flow stream at combustion product release. And one more important task is taking into account the moisture condensation, because combustion products consist a lot of water, and during the process and during the heat transfer, we observe condensation of the water on the pod surface. Now, this process we don't take into account, but it will be our further tasks and will be a further investigation. In conclusion, I can see that we are very close to the development of final model, which can be very efficiently used to predict regimes of thermal process of plastics. And of course, this process requires a lot of experimental investigations and a lot of simulations. But I think for now, this model very realistic represents a real process inside the chamber, which we observed during the experimental investigation. That's all. Thank you for your attention. If you have questions, please ask.
Thank you very much, Oleg. Please put on your screen first page of your presentation. I have not get needed photo for our report. Thank you very much. I did it. And for who will be interested in, on your first slide, there is no the title of our project, but if we remember it, that it is increasing efficiency of the using green hydrogen fuel mixtures on treatment technologies processes under or focused on plastic treatments. How can we say about useful or not this type of we have not talked about another fuel mixtures. Why do we need to use what the pros and cons of using green hydrogen, and what the initial condition of the started of the process? I mean, low pressure and so on. May you please repeat it one time?
Of course, our work is very important. I mean, in the aim of increasing the efficiency of treatment using green hydrogen, because first of all, our models allows us to decrease the number of experimental investigations, and of course, our research allows us more exact choose regimes of processing, and of course this increases the total efficiency. We will use less fuel mixture, we will get less combustion products released into the atmosphere. We finally very positive we actually increase total efficiency at all, because as I say, we use less fuel and we increase final productivity of the processing. So
yeah, thank you.
It's very important.
And we have performed together with Vadim experimental experiments on our plastic parts using the hydrogen with Poland colleagues. So it's also experimental application.
Thank you. Attila, let's join us, please. Do you generate any questions for us?
No, thank you. It was very interesting. Thank you for considering me. I don't have any questions now. Thank you. It all clear.
Thank you very much. Actually, our project comes and on the end of April, so we have to prepare a report, final report, maybe some Andrzej Teodorczyk.
If
Hello,
you have any
Professor.
questions so that I can help with the report, just let me know. I would be happy to read it
thank you
or
very much.
add some comments if you like.
Yeah.
We're so glad to see you, Professor. Andrzej Teodorczyk, our biggest partner from Warsaw University of Technology, Technical University, sorry.
Yes, good morning.
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 Good morning.
Dear Professor, do you have opportunity to join our meeting tomorrow at 11? Or 11, I mean, by Warsaw time.
Okay.
Will it be possible?
Yes, sure.
Super, because today we had to start more earlier and we are near the finishing.
Okay.
So we had a presentation as well, but tomorrow we will repeat and discuss some additional questions to prepare the materials for publications.
Okay.
About detonation waves and so on. For today, that's all. I would say very or much grateful for being present in here and presentation the results. Thank you very much, Attila, as find the time for join us. Thank you very much at one time, and I will stop recording.